secret of me. I do a little bit of recording in the class, and I put the video up on YouTube just in case you want to look back at any of it. Not too much of that in this, because once we get deep into the practical, that's more you having a go and not me standing up here talking. Okay? So, foundation degree module, programmable logic controllers. Just go through an introduction. So, learning outputs. When you've completed this module, what you'll be able to do, or prove that you're done, is explain the design, architecture, and operational characteristics of PLCs and that interface into the systems they control. So you'll kind of understand a little bit about the internals and how the outputs and inputs facilitate you taking information from the real world, processing it, and then making the real world do something different with it. It's as simple as I can explain it at this stage. You'll also be able to explain PLC to PC and PLC to PLC communication techniques, the use of human-machine interfaces, HMIs for short, SCADA software, and field bus systems and their applications. So essentially, networking with PLCs. Yeah, more complex systems. Those two learning outcomes are the subject of the assignment for the module, which, as the assessment will get out of the way, or get processed in the early part of the module. Can't remember the exact dates, okay, but I think I issue week after next, and then there's a 4-week window to hand it in. All right. Then, thirdly, demonstrate the techniques and languages available to assist in the development and construction of PLC programs. So you will be given a final task to write a program for a piece of kit, and that's how you'll prove that you know how to do that. All right, and that will be assessed. And you'll apply PLC programming techniques to produce, test, debug, and demonstrate a control program for a given application. So you'll actually do all the documentation as you would as a real project, and write some testing routines and use them to make sure that it actually performs to the specification. Yeah. All right. One thing I need to cover with all of you guys is there's changes to assessment regulations this year. I'll just turn that off for a minute. Learning outcomes 1, operation and architecture, and outcome 2, communication and interfacing. That one used to be 2 assignments, but I combined them together because that was difficult to fit them all in separately and give enough time, and that took me twice as long. You know, it only take me about quarter as much time on top to do it in one assignment mark, and then that to do 2 separate ones. All right, so that's much better. And then the second assignment, the first assignment's only worth 40% of the mark, and the programming assignment is worth 60. So you've got weighting on that second assignment as well. All right. It's got to be at least 50 instructions, and the program I give you is easily that. Okay. I mean, I've had 2 or 3 people say to me, I'm going to try and program your application in less than 50, Mike. And with both the applications I've ever given, nobody's ever been able to do it. All right. So, brief history introduction to PLCs and what they are. PLC was first developed by General Motors somewhere around 1968. Prior to this, in the 60s, production lines were usually controlled by relay-based systems. Well, when I was in industry, back in the 80s and 90s, they still had relay control systems then, and probably still in some places have got them now. All right, but that was the idea, to kind of try and replace those. Complex production lines using relays present a range of problems, and if you've ever worked on complex relay controlled machines, fault finding wise, like I have, you'd understand what I mean. Reliability was getting worse, because a large number of relays involved. Some cubicles with over 200 relays were quite common, and I'd guess our blow mould and machine panels had that number of relays within the panel. Maintenance problems increasing due to the complexity. If you've got 200 relays, there's a total of over 1,000 contacts in the circuit at least, each having at least 2 connecting wires, resulting in well over 2,000 cables. It's a lot. A fault in any one of the contacts or cables very difficult to trace, particularly an intermittent fault. Yeah, and you're trying to find where that wire goes. Is it in the right place? Which contact number does it go to, and so on. Okay. Difficulty carrying out any changes. So this is the other big thing. Make a change to a relay control system usually means drilling into the panel, mounting more relays, cutting holes in the front panel so you can put a timer in and such like. Okay. Often relatively small change in the control requirements would result in a complete rewire or significant rewire of the control panel. Yeah. So that's back in the day, back in the old days. PLC was designed as a replacement for those relay-based systems. Original target for that was that there would be a system that could be easily programmed and when necessary reprogrammed. PLCs can quite easily. A system that's solid state based on transistors and integrated circuits, capable of withstanding harsh industrial environments. A system is more reliable and easier to maintain than relay-based control systems. Plant downtime, costs reduced, that type of thing. That's what they're looking for. And a system smaller and more cost competitive than the relay panels that's designed to replace. Okay. Now, I would, in my experience, say yes, they could probably make the panel a little bit smaller, but quite often you still need quite a bit of ancillary kit external, like contactors. If you've got motors and large loads, the PLC won't switch them directly. Yeah, so you've still got some heavy contacting gear, but there's a lot of like control relays replaced. So you maybe could, I think, you'll perhaps cut a blow mold panel down to somewhere between 1/2 and 3/4 of its original size by making a control system PLC. But it's a fallacy to say you can just put that tiny little PLC in there and you've got all that space for nothing else in it, because that wouldn't be true. All right. In actual fact, this is PLCs versus your personal computer. The technology used in a PLC is the same as that in a PC, but it's an industrialized computer, capable and used on the shop floor. And I know you do see PCs on shop floors sometimes, but these can go in some really quite harsh and remote environments. Right? It has the advantages in control situations of being relatively easy to understand and quickly modified. The programming that we're going to do is going to be in ladder logic, and it's, if you can understand relay control diagrams, push buttons, relays and contacts, you can convert that knowledge over to a ladder diagram relatively easily. A relatively fast response to process situations, so they'll respond quickly, they run fast. Wide range of timer and counter functions dependent upon manufacturer. Bottom end range viable in cost-wise to replace systems with 4 or more relays. So they've got the cost of the lower end down really, really low, because a single relay is quite expensive, and so that it's cost effective to replace quite small systems of PLCs. Special interfaces available to handle analog signals, high-speed digital functions, temperature, etc. And there's a range of simple operator and more complex operator interfaces available, BIM machine interfaces. Yeah. so your operator can interact with them. So your PLC, in comparison with PC, is designed and packaged for an industrial environment. That's well sealed up. I mean, yeah, it's got something to allow some air around it, but it's designed to work in a harsh environment. The inputs and outputs are isolated from external systems to protect the computer from external voltage sources and currents. Programming a simple ladder diagram representation of circuit rather than a complex software language like C or Pascal or any of those other what I call medium level programming languages. Recent IEC 1131 standard, I don't know how recent that is now, to be honest, introduced other methods such as structured text, sequence charts and function block diagrams. I stick to what I know, which is ladder diagram, and I think in essence that's what people who have got to look after this kit understand. You know, the engineer who's doing maintenance down at Birdseye would understand that more than any of the other languages. All right, and ultimately all those ways of programming, when you actually convert that program, you're actually turning it into exactly the same real code to that processor, whichever method you use. All right. The way the PLC treats the stored program in what's called a continuous scan is different to the way microprocessors behave. Microprocessors, they appear to multitask all the time, don't they? You think you're doing the same, lots of different things all at the same time. PLCs don't tend to work that way. They go through a very defined sequence, and the reason for that is so that defined sequence takes the same amount of time each time and every time, which is important to a controlled system. You want to know how long it's going to take. Yeah? All right? So, different types, unitary and modular PLCs. So, the lines, you need to be careful with this because it's a bit in the assignment better, but the lines between what I'm making out as three different types are very blurred. You can't say, it's difficult to say with different manufacturers that go with that and that's in that bracket. But there are kind of three general types out there. Unitary, tiny little brick-like PLCs. They're only really that size so you can get the contacts on them to connect your kit to. Right? Usually provide little or no scope for expansion once you're bought that one, that size, that number of inputs and outputs, that much memory, that is it, usually. Okay? Can have the advantage of being very small, but they're the ones that are economical to replace small systems. Then we get what's called the modular type. This is where FX1Ns, you're going to be using FX3Gs for your programming. Okay, this is where you buy a base unit that's got input and output on it. It's got the processor all inside. It's got the communications you need to program it and so on, as well as some input and output availability and some memory. Yeah, but then you can add in Mitsubishi, which is what we're going to use. You can add to that up to 8 extension modules. There is a cap on the maximum number of inputs and outputs combined. I'm not going to state that because that's one of the things I'm asking you to write about in your assignment. Okay, so you're being asked to go and find out. But there is a maximum, but it can be in up to 8 extra modules, so you can do additional inputs and outputs, analog in-outs, motion control and comms are typical things. These expansion modules you can buy separately, so you can buy them afterwards, and then they connect together either by clipping on the side or via connection between them using ribbon cables. Okay, so that's like a a go-between. Having said that, if you design a system and put one in, and then you decide later that you want to add something to it, you will need to have left room in the panel to do that. Otherwise you won't have space for it. Okay? Let's start off with unitary being the cheapest. These are mid-range, and you can pay like 1,000, 1,500 quid for them. That's a price off the top of my head, depending on how much IO you use and so on. Okay. Then we come on to the big pucker jobbies, the ones that cost a lot of money, right? You've probably got them at Birdseye. Yeah, Alan Bradley? Yeah. So they're kind of one of the most popular PLCs out there in big industry. Yeah. Well, depends whether you're used to them or not. But they try and say that all of them do programming in the same way, but they're all the same but different. So these are rack mounted. So what you do is you buy a rack, and then you choose a power supply separately, a CPU card separately, and all your input, output and communication cards separately. You plug them onto the rack and you connect your wires into them. The advantage of that is you want super fast CPU, you buy a super fast CPU. If you don't need a super fast one, you don't have to. You can buy, I've worked on a machine that had dual CPUs in a PLC, so it had two processors. If you've got a lot of current need for your inputs and outputs, you could buy a high rated power supply and so on. So I'm only guessing, but I'd say a minimum spec that's got kind of a slowish processor, reasonably low memory, a power supply and an input and output card, probably at least 1,500 quid. At least, if not a couple of grand. I don't know. I've been out of the loop for a long while on prices, but they are expensive. Yeah. And then you can connect to one rack, you can have a lead and connect to a second rack, so you can put even more in. There are limits. I don't know what they are off the top of my head, but they're pretty high. You can have lots of I/O on rack-mounted PLCs, but you've got to justify the price. I expect you got them running whole production lines, didn't you, Dom? Yeah. The whole factory or something. They're SCADA'd together, are they? Yeah. 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 So you back up rather than dropping stuff on top of each other. Yeah. 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 Well, that was a bit of the trouble I had with the PLC as a Japanese manufactured PLC, but that had two processors, because I was the engineer who went out to Japan and I learned about these things, and they learned that I was a good PLC programmer. So our engineer left me his lead and gave me the software so I could actually interrogate the program. The problem was I didn't have two laptops with two lots of program and two leads like they did, so they could look at both programs at the same time. That's in that now that's linking with this program, so you turn that one off and load the other one, constantly going backwards and forwards between the two programs. So it's not easy. You're right, it isn't easy. And that documentation was quite poor. There was 80 pages of ladder diagram without one cross-reference or anything. That was just numbers. So that made it difficult too. Right, I've digressed, moving on. Okay, so to provide maximum performance, most manufacturers use rack-type construction. So you can get a variety of rack widths that will take designated numbers of cards, okay, and then you choose from what cards you want. So you can buy cards that are just input, just output, analog input and output cards, temperature control, positioning. There's various safety relay kind of input-output modules available these days that I know nothing about because I'm not in industry anymore. But they're out there, and you simply plug them onto the rack to make the connection between the card and the CPU, so it can communicate, and then you connect your wires in to the front in the normal way, and away you go. To aid further expansion, you can add additional racks, and the rack size can be selected to allow for future expansion, so you haven't got this "have I left room" business. Yeah. Sorry? Yes. Yeah. Well, they usually have 16 on a card, in my experience, for rack mounted. So 16 points on a card. Yeah. So if we just think a little bit about the selection of a suitable PLC for a task, we'd want to know how many inputs we're going to need and what their type was. A bit more about that later. Required number of outputs and the type required. If there's any requirement for expansion capability, and you'd be an absolute fool if you went round a piece of kit you're fitting a PLC to and said, "Oh, I've got 16 inputs, I'll get a 16 input card and no more for my PLC." You'll always forget something, and someone will always want you to add something on later. So even in the first instance, allow a little extra. The power supply, what program storage capacity, which is usually in the number of program steps that you can have. Program processing speed, whether you need any networking capability to connect PLCs together or to connect to a wider network like a SCADA system, and program and software. So if you work for a company that manufacture things that have got PLCs in them, do you want to use a lot of different PLCs where you've got to buy lots of expensive software, or you want to encourage your people? But then you get a company like Birdseye that will insist on Allen Bradley, because that's what they got, pretty sure.
Yeah, that's pretty much all.
Pretty much.
And then we're all doing it away. It's quite complicated to go through. And we've got a lot of German manufacturers as well. Now,
Got Siemens, yeah.
we've got a couple of Siemens PLCs, but all of these
Allen Bradley in, yeah.
we don't know why we did it because they don't understand Allen Bradley. They only understand.
Yeah, there's two sides to that coin, in other words, yeah. You've got what you want, but that ain't been designed in the best way. Yeah. There might be, like I say, there might be a preference for manufacturer, and above all, you're going to take into consideration cost. Yep. So we're talking about maybe for the little low-end ones, a couple of £100 maybe. I don't know. They might even be less for that. Modular, between that and £1.50, £2,000, and the rack mounted through the ceiling. Yeah, your choice is the depth of your pocket. All right, programming software. PLC manufacturers generally have their own proprietary software. So SRS links with Allen Bradley, I believe. Yeah. We have, there's 3 different ones from Mitsubishi. GX Developer, right, that's what we're going to use. It's the base level ladder logic, sequence function, programming and documentation software. Okay? We don't need all the bells and whistles that are in the other 2, and they just complicate the issue for what we need to do. All right? Then there's a mid-range called GX Works. You've got PLC ladder logic, which essentially GX Developer sitting inside that GX Works program, but it can handle multiple PLC programs in an integrated workspace environment. So you can be working on multiple programs at the same time with that software, all in one project. So you can save it all in one go, and it kind of handles that in a more integrated way. You're only going to be writing one program at a time, so you don't really need that functionality, and I don't think we got it anyway. Right? Actually, we have, but we're not using it. And then there's IQ Works. This is a high-end integrated workspace based on programs that incorporates and facilitates and manage multiple projects across PLC drives, motor drives, and HMIs. So you can put all your HMI, motor drive programming, and PLC program all into one package and work on all of it in an integrated way at the same time. Again, we don't want to do that, so we're not using that software, and we definitely haven't got IQ Works. All right? So on this course, you'll learn to program and write documentation with GX Developer. All right? Has anyone had a go with GX Developer before? You've done GX Works, have you? Okay, yeah. Well, you've touched one, that's the main thing. Is that with Mr. Edwards? Yeah, okay. You as well, Kelsey? Did you do PLCs, Lewis? For Phil? No? Mechanical? And have you done anything, Nathan? Right, quite baffling. Right, have you all got a USB storage device? Yeah. Right. Some very important device up front. Yeah. Before starting the program, an important point about GX Developer projects. They consist of multiple files. Right? They aren't one file. You should not be trying to open a GX Developer project by double-clicking like you do a Word file. You need to go into the program, click on the Open File, and navigate to where you stored your project and open it that way. Yeah? Otherwise, you may well have problems. And you want to create a folder to put your PLC programs in, and don't put anything else in that folder. Because when you save a project with something like Dom's first project, it'll actually create a folder with that name and then put all the files inside it. But the GX Developer software will recognize that as a project with a special icon rather than a folder. And you'll see what I mean when you actually have a go with it. All right? Don't save your programs on the C drive. Navigate to your, it'll usually be E drive for your plug-in USB, and save it on there. And then also back it up onto the network so you don't lose anything. All right? So don't try and open by double-clicking the icon, because it don't work very well, if at all. So, if you create a folder on your USB drive for PLC course or similar, store your associated documents, and then inside the PLC course folder, create another folder to put your program projects in. So keep your Word files for your assignment and your program separate. Alright, that stops you getting into muddle. That's not a very big class, but big classes, I usually get at least 2 or 3 people ignore that advice, if not more. So, what you're going to do in a minute is obtain those 3 pieces of kit. Yeah? And we'll have to get a laptop. I don't know if Chris has left the key in here for me, but you'll need a laptop. So, I'm going to get a PLC rack with an FX3G PLC on it. We'll work on that table in the middle there, practically. Keep away PLCs away from this area. Alright, you want a kettle lead so you can power up, and you want one of these switch boxes so that you can actually have some inputs and outputs. So you've got some switches and some LEDs. That's the kit you need. These two blue plugs go in on the front here. You can't get them the wrong way round because one's male, one's female, and it's not possible to connect them in correctly. If you've got an extra plug on your PLC, that'll be because that's got some analog on, and that D connector is a completely different size, so you can't plug these into that. Okay? So that's what you're going to be doing in a minute, in a little while, is getting that kit and getting that set up. When you open the GX Developer software, initially, just about every icon is greyed out because it's not available. The only thing available is New Project and Open. Yeah. So that's what will happen. What you've then got is a project navigation area, which doesn't show anything until you actually open a project, and then the ladder diagram area, which is where you do your programming. All right? And then, when you start a new project, these then light up because they're available. A lot more of the icons are available. You get something in your tree over here as regards to the project. It's currently set to the main program. And there's one instruction that's always in the program. That's a straight line to an end instruction. Yeah. So current cursor position has got a blue square. Okay. And there's the end instruction in there. And you can't delete the end instruction. You can't put anything after it. When you put something else on top of the end instruction, it just moves it down one line. So I'm going to give you the notes in a minute. And I'm going to get to that stage and continue from in your note pages, set up your first program and practice entering ladder instructions. Okay. So this week, don't worry about whether you understand what that program does and how it does what it does. The idea is just to familiarize yourself with GX Developer and have a go, right? And then next week we'll start to look at programming and define how we decide what to do to make the PLC do what we want it to do. Yep. What I would suggest is, yeah, get the kit out and I'll get the notes over to you. All right.